Let's go ahead and get started today. So welcome back. So what we're focusing on, ensemble learning. All right, so let's talk about our goals for this session. So what we here are going to explore the general methods of max voting, averaging, and a weighted average. So we're going to think about some general ways that we can get information from an audience. From there, we're going to use Jupyter Notebook with Python 3 to create a sample data set. Discuss different models to experiment with individually. So we'll work on some smaller models. We'll see the general import statements and talk a little bit about each one, about the differences between regression and classification, for example. We'll discuss the benefits and purpose of stacking. So again, you guys pretty much summarized it perfectly in the chat there. If we want to make our best predictions, and oftentimes that means choosing more than one model. And then what we're going to do here is we'll utilize our stack model to optimize our data analysis. You all should be able to view this directly. I'll be using Jupyter. This is Google Colab. It's just an online version of a Python editor. I would suggest staying in Jupyter though. That's what I'll be using for this demonstration, just because then it'll look the same and Anaconda has all the same installs type thing. So if you're in some reason you cannot get this on your side, so this is the notebook that I'll be kind of dumping code into. So as I do something, I'm going to actually copy and paste what I type on the screen into this notebook. That way you can have it in there as well. So for example, in today's work, we have a ton of imports. This is just a copy and paste, like do Control A, Control C, or if you're on a Mac, Command A, Command C. That way it avoids us having to type all this in. Also, as always with imports, there's like inherent spelling errors. So I did run this right to make sure that they were all right. So we're good there. Okay. So hopefully we can all open that up now. Again, so what I'll be doing as I'm typing something in here, once I get through and we've explained it, I'm going to copy and paste it and just dump it in here. That way you guys have access to that as well. So if you've got that open, what I'm going to ask that you do is go ahead and just copy and paste all of those imports into here. So into your Jupyter Notebook, and then you could just go ahead and run it. And while you're doing that, I'm just going to kind of briefly talk through the different ones we're going to be seeing. So couple of the usual ones here that we're going to see. You'll notice we're not working with pandas necessarily today, which is another one. So if you're looking to have yourself like a master list of cool imports, I would just say up here, the ones we've seen yesterday, like matplotlib, you could put those in. So you want to build up your list of these things, just because I will say a good habit in forms of coding is to get used to what kind of imports you need for what. So we'll be using all of these today to learn about ensemble learning, just to kind of expedite things in our coding. So we have NumPy, sklearn. Sklearn is a great machine learning package. There's others out there. That's just one that I kind of have always stuck with. It's also nice just because you'll notice that there's a ton of other like resources and tutorials online as well for that. And then here's our different things. So we're working with both classification and regression today. So something cool here is these two little pieces. So if you're ever trying to build up demos, like good practice data to work with, this is actually, you can make classification and make regression data sets. So this is a nice way of, if you don't have data, but you want to try something out, we're going to show these today because that's a question I always get of, where do I find data to work with? And in in a perfect world, you'd have some of that real world data, but it's also nice when you're trying out a new program, you're trying to build yourself a repository, to be able to use these two here of make classification and make regression, because you can build data sets that you need in real time. Okay, so with that, let's go ahead and do some demos here. So the first thing I want to work with here is some examples of getting the general idea of what ensemble learning is. So I'm going to zoom in a bit on my screen just so you guys can see easier. All right, so first thing we're going to do here is we're going to talk about what's called max voting. So we're going to talk about max voting, averaging, and a weighted average. So when we think about these things, let's go ahead and build ourselves some ratings of a performance. So let's say, someone did a whatever it may be, and they were graded on it, so we got our ratings. So let's go ahead and make a list here. And we're going to say ratings equals, and just a list, let's say 10, 9, 10, 8, and 7. So we had 5 different raters, and these are the ratings that they received or reviewed of a certain performance. Now, when we think about this, the idea of a max voting. So max voting, simply put, is taking the mode. It's taking the one with the most occurrences. So a way to get that is we could use that import we had of mode from SciPy. We could just say mode of ratings. So when I execute this, it tells me both the most popular vote or the frequency of 10. So that's telling me, okay, here's my array. It's just this number 10. That was the most common vote, and it tells me how many times it occurs. So max voting is considered that. Now that might be informative. We could say, wow, like the most common score this person got was a 10. So that's one way where we look at the most common occurrence. So we look for the mode, that is max voting. Another one could be taking the average. So if we want to get some practice in with definitions here, instead of using just like a dot average or dot mean, let's go ahead and create a custom definition here. So we could say the definition of average is going to intake a list. And then I could go ahead and say, I want you to return, I want to sum the list, and then divide by the length of the list. So that's creating a definition for this. Now, again, there is a million other ways to get the average quickly, but whenever I can, I like to throw in little snippets of, creating definitions. That's something where a lot of times there's so many pre-built modules and packages, you get away from it. But again, the practice of getting your own definitions once in a while and being used to applying them, writing them yourself, it's just really good practice to continue to use. So let's go ahead and use that definition now on our list of ratings. So I'm going to say average, and then I want to do it on ratings. So I get 8.8. So that found us that average. I'm going to go ahead and start adding things to our notebook there. So I'm just going to go ahead and copy over what I've done so far. So if you do get an error, I had some good feedback from everyone on that yesterday. So if you get an error on something or it's not working like it is on mine, that's going to be the place to go. If you use that online notebook I made, you can just copy and paste from there. All right. So we had two different ways now. So we looked at the mode. We said, okay, the most common thing's 10. My average is at 8.8. One of the cooler ones here is going to be our weighted average. So I talked about when we work with a weighted average, there's a lot of different ways to, create a program for this. There's some pre-built stuff. So what we're going to do today is we're going to go ahead and just write out a nice one-liner here so you have a cool weighted average calculator on hand. So weighted averages come in handy when certain things are deemed more, I guess you could say, important in a group. So for example, whenever you work with population data, cohort sizing is important. You need to work with the different sizes of a city. That's what, for example, a lot of data is given per capita. So if I looked at, for example, renewable energy resources and like compared how states or countries use them, it's really based on per capita, because depending on, if you have a very small town, that might look great. But if there's only like 10 people out there, it's not really going to be as impressive as when a large city does something like that. So again, that idea of per capita and then figuring out how to quantify that. So weighted averages come in handy like that, just because they help us get a better understanding of the data when your groups have inherently different sizes. So again, population data is a great place to use this for. Now, how we could rake this in here would be the fact that maybe our raters have different levels of expertise. So our judges, we have 5 judges who delivered these 5 different scores, but maybe our last 2 judges here, so this is judge 1, 2, 3, 4, and 5, maybe judge 4 and 5 have the most experience here. So I'm a little more concerned about their evaluations as opposed to the first 3 who may be newer judges and just really good at giving those high scores. So what we're going to do here is we're going to create some weights to use alongside that. So make a list of weights. So let's say we give the first 2 are just going to be, or the first 3, they can all have 10%. So 0.1 is a proportion there. So that's their weight. So their vote is only worth that amount. Whereas those last 2 judges, they're real experts. So we're going to go ahead and give them 35% of the weight. So by creating these weights, we give them more importance in their vote. So now these last 2 votes, and notice the order matching up here, and the way we wrote this is that's the order that it's going to go in. There's also a way you can adapt this as well to work with like data frames. We'll see that later on, of nice ways to work with that data as well. So not everything has to be a list. All right, to do this, we're gonna go ahead and build a nice little calculator here. So I'm just gonna call it weighted average. So as opposed to doing a definition, we're just gonna go ahead and define it this way. So we're gonna say sum. What I'm gonna do is I'm gonna say weight times value for weight comma value in zip, weights, ratings, and then we're gonna go ahead and divide that by the sum of weights. So this is doing a nice little lambda or an anonymous function here is another way to do it. So as opposed to a formal definition, we're just gonna do it here in a nice one-liner. So this is customized to work with, as you can see, two lists being inputted. So we're gonna do weight times the value, and then I'm zipping those together. So I'm putting those two lists, merging them side by side. So again, they go pairwise. So let's go ahead and run that. And then what we want to do next is just print that out. So let's actually go back and edit this and just go ahead and print that out. So I can say print weighted average. There we go. And I'm gonna go ahead and update our little online code repository as well. So these three different things here, and why we worked on these little exercises is to kind of see like why we use different rating systems now, because none of these are inherently the best. So if I think about it here, like if I'm looking at this and you just kind of figured like you'd say this person did pretty well. It's like, okay, like that's, you know, they have 2 10s, a 9, like that rating must, if it's out of 10, that's really impressive, right? They're pretty high up. But then we see here, when we just take an average, it brings it down a little bit. Now 8.8 is still pretty good, right? We said, okay, hey, that's, you know, the mode gave me a 10, 8.8, still pretty close to 9, right? But then when we looked at a weighted average and said, well, okay, but we're really only worried about what the last two judges think, then it brought it closer to just that value of 8 because they had those inherently lower scores. So as we consider this, the idea of ensemble learning would be, hey, is there a way that I can combine all three of these together? You know, maybe I could use ensemble learning and then take the average of these. So maybe if we wanted to figure that out, the idea of just getting a summative rating of looking at 3 different ways, we could say, okay, the first one came as a 10, the second one came at 8.8, and the third one, if we round it here, we could say is 8.15. And then if we divided it by 3, maybe this is our best rating. Maybe that 8.983, maybe by averaging and combining all 3 of these ideas together, we get the idea at the heart of ensemble learning, which is methods give the best vote when they're combined together. And this goes into that thought experiment that I'm sure you've studied or heard of, where, you know, if there's the number of beans in a jar, for example, no one person is probably going to get it right. But if you had about 100 people guess and took the average, it would be very close. So the idea that, you know, everyone's perspective combined together gives you a better idea of the actual answer. So that's where we kind of get in the idea of ensemble learning here with this. All right, now let's get into something a little more advanced here. So again, I'm going to keep, as I type, I'll type, explain, and then I'll go ahead and copy and paste it over to that repository as well online, which you'll have a link to, just so that way if we, you know, get stuck on anything, you can always go back over there. So first thing we're gonna do here is just check your sklearn version here. So I want you all to type in print sklearn __ version __. So you need to have at least the same as mine. If not, you're gonna want to update, but if you've all downloaded this recently, you should be good to go. So that's just to make sure all these packages will work in yours. But if your imports worked, you should be good. All right. Okay, so first thing we're gonna do here is build in some different levels of models. So I'm gonna go ahead and take some notes in here as well, just so we have it. So we're gonna say what a level 0 model is. So So we're going to start off with a level 0 model. So this is the idea of intaking data directly without having that ensemble aspect of learning from the previous models. So that's where that idea comes from of we want to build up how to have them learn from the previous models. So first, we're just going to create something where they don't learn from that. Whereas a level 1 model would be considered it learns from one previous example. Level 2 would be learning from 2 previous. So the level just corresponds to how many models it is learning from. So let's go ahead and define it. We're going to say models, and then we're going to go ahead and make a list here. So let's go ahead. I'm going to go ahead and type this out just to make sure it looks right, and then I will explain what we're doing. Okay, and I'm going to go ahead and throw that over here in our online thing as well. So what this is doing is it's creating a list. So it's defining models as a list, and we're pulling in 2 different level 0 models. So logistic regression, and then SVM. So these are the imports here. It's actually called SVC in the import. And we're making a pipeline of it. So what it's going to do is for this one, when it executes, it's first going to just standardize the data. So a standard scalar. So to normalize it, and then apply that SVC component there. So these are 2 common models that we see when we're dealing with some classifications here. Now, we also need to make some data. So I'm going to go ahead and type this next round in here of our stacker, and then we'll go ahead and let everyone get caught up there and making sure we're caught in on this. So here we're going to say stacking equals stacking. And then next we'll go ahead and make some data. Okay, awesome. Thank you for the feedback in the chat. So the code here in line 12, what this is doing is we're creating a list. So whenever we see these square brackets here, that's going to be a list in Python. So the first 2 things it's doing is it's pulling in these 2 models. So our first model is here. That's going to be logistic regression. We're going to use this to do some classifications here. So I'm just building a list of models by putting them all together. And we'll see a couple other ways to do this as well, but this is one of the more direct ones. For this one, this is the other model we're looking at here in our list of models. So it's SVC, so secure vector classifier, and then we're using a standard scalar. Just for this one to work, it so happens you need a standard scalar with it. You don't need that with all models, but for this one you do. So just think of this as creating our 2 models here, 1 and 2. And then our stacking classifier is just putting those 2 together. All right. What we're going to do now is go ahead and make some classification data. So to do that, let's go ahead and say x comma y equals make underscore classification. Let's say for our samples, let's do 1,000. The number of features, meaning how many different columns relate to them. Let's say maybe we got 20 of them. The number of informative, meaning the number of like useful columns that are going to actually help our model. We're going to say that there's 15 of those, so 15 of the 20. And then the number of redundant, just making sure I'm spelling everything correctly, we'll say that there's 5. So again, I'm looking at this here. The number of features refers to how many columns. And then the informative ones mean like how many are useful in our modeling. And the redundant is like how many are just kind of extraneous data that we don't actually need. So just to kind of simulate here what a real data set might look like. And then the last argument in this is going to be random state. I just use 1, pick your favorite number here. It's just a way of making sure that whatever you create for this data set, it's always going to be the same. So whenever you're building data to practice with, you always want to include a random state argument, just because it's like, for example, let's say I don't have this in here. Then every time I run this notebook, this data is going to be new. And it's like, well, that doesn't really help me build a model, right? Because maybe I run this with random state 1, and it just so happens that that data is like really easy to classify. Whereas then when I run it again, if it's new data, I can't judge any refinements on my model. So again, whenever you're building data, I suggest you use a random state thing there to make sure it's just going to stay the same. And then lastly, what we're going to do here is just kind of look at the shapes of our data. So let's go ahead here and say print. And then we're going to say x.shape. And then let's get the y.shape as well. So I'll go ahead and put it over. So what this is going to do is it's showing us our things here. So our X data, so what we would consider the data we're learning with, versus the data in the Y, which is what we want to classify to. So we just put those two side by side. So we can see there's 1,000 rows with 20 pieces of data in here. It's just 1,000 rows of data, and it just gives us our classification or what we want to aim for. So this is just the example of how we were going to go ahead and make one. So if I applied this, we could use those models, and then we could see which one did better. But again, that level 0 idea, this was more of just an example to have handy. We're not actually going to be using this because, again, this is Ensemble Learning. So we want to learn how to build something that's going to be a bit more powerful. So to do this, let's go ahead and create a definition here. So we're going to use a definition in order to get all of these different models in at once. So this one is going to take a moment. So I'm going to go ahead and type this out, and then we'll talk through it. All right. So sorry about that pause there. Whenever I type out something with a lot in it, I always try to really make sure I don't make any mistakes, because there's nothing worse than, like forgetting an S in something and then it's saying there's an error. So what this definition is doing, and that's why we kind of worked with it earlier, it's formalizing a faster way of doing things. So it's avoiding having to customize models like this. You'll also notice for this round of SBM, this was an example of if you needed to make a pipeline to standardize things. So what a pipeline does is it just combines a couple of things into one. So if you ever need a standard scalar, this was more so just a handy note of an example. We won't need it with this data, just because, again, we created it. We know that there's no need for standardization here. However, if you ever need to standardize data, so like, for example, in yesterday's lesson, we've seen that we had some really large values in there. So sometimes if you need to standardize up front, that's a cool way of doing it. However, we won't necessarily have to today. So we're just going to keep it clean here. So if you needed to make a pipeline or anything in here, you could do it in the same way here with each of these by using that make pipeline command. So what this definition is doing is it's going to get some models for us. So it's going to create a dictionary first. So it's the models equals dict. So it's making a blank dictionary. And then it's putting in some pairing values. So this is just shorthand ways of calling the models. These are just acronyms I typically use. You'll see some of them out, but this is just kind of a standard way people would name these different models just for the shorthand purpose of them. So it's calling in 5 different models: our logistic regression, our neighbors classifier, decision tree classifier, SVC, and then Gaussian NB. So that stands for Gaussian naive Bayes. So if you've heard about Bayes theorem before, it's a really popular thing that we use in pretty much everything. So with these models in there, what we want to do next is go ahead and look at a way to evaluate them. So what we're going to use is cross-validation. So we are going to evaluate models with cross-validation. To do this, so I'm going to go ahead and type out, then we'll explain. All right, I'm just going to paste that over. Okay, so with this first thing, I'm always going to reference is, even though right now I'm throwing this code in a repository, that should be like your backup plan. Like if something doesn't work when you're typing it in, the only reason why is because a lot of students who are early in data science, what I've noticed is that they get a lot of really cool stuff they might be able to find somewhere, but in any tutorial, I know it sounds crazy, but like being able to type code yourself is just good practice. Like for example, this one right here, repeated stratified k-fold. The capitalization is important. That's the name of that specific package we can get from that module there. So getting used to that is something, again, like because I find myself sometimes I'll be like, okay, like I get so used to copying and pasting from my own code even that like when I have to actually type something, like it's that really paying attention to what you're doing there to avoid those errors. So I'm going to go ahead and run that, and then let's talk with taking samples of it. And then how many times we want to repeat it. So going 3 times on that, and then the random state being 1, just so again, our splits of the data are consistent. So when you're applying this to different sets of data, again, you always want to keep that random state in there for consistency in your model evaluation. I remember early on when I started working with stuff, I would get so frustrated because I didn't understand the point of random state. And then I would, keep running a model, and, sometimes I'd run the model and be, 95% accurate. I'm like, wow, this is awesome. And then I would go back the next day. I would come back and it would just, be a different score. I'd rerun the whole code and it would come down at 72%. I'm like, what happened? I didn't even change the model, kind of thing. So again, using that random state is beneficial there, whether it's created or real world data. So for the number of models, I'm assuming you're talking about up here. We're doing this example with 5 just so we can see how it can go off of. These aren't going to be like terribly resource heavy. When they get applied, it's more so going to be dependent on how large the data is. So our data set here has 1,000 rows with 20 features in it. So if we think about multiplying how many individual values there, we'd have about 20,000 data points to be evaluated. For number of models, I would truthfully say the more you want to try, the better. These are just 5 very common ones we use. However, there's some models that are so hyper specific, they're really only going to work with certain kinds of data. For example, it's like if you're dealing with an exponential distribution, there's going to be some that work better than others. However, these are 5 of the most common ones I'd use. If you're worried about that, I would look over in this more so about like computer power and stuff. Your repeats then kind of keep that to like 3 to 5. It's also not going to do a whole lot of difference when I've run similar programs with this with like early on, I thought, like, oh, I'm going to do, 100 cross validations to get my model to the best it possibly can be. That sometimes eats up a lot of RAM and takes a little while. However, with what we're running here, so the number of models isn't going to like drastically make a difference. The biggest thing you'll notice is that it might take a little longer on your device, depending on, how much RAM or what processor you're using. So great question there in the chat. Thank you for that, Larry. All right, so we got our evaluation model here and how we're going to look at the scoring, how we're going to figure out which one worked well. So the next thing we're going to do here is we already have, let me just check where we're at. Okay, we got this, we have our data set, fantastic, we're good there. All right, so let's go ahead and put a little more together here. So what we need to do is, did we make this a definition? Okay, let's go ahead and change this a little bit. Let's actually go back and make a definition here. So I'm just going to go ahead and edit my line 14 here. And we're just going to create a definition from this. So we're going to say a def here. We're going to say get dataset. This way our model will just run faster, truthfully. And then a nice little shortcut way here of getting this is let's just hit backspace a couple times and then enter. And I'm going to paste this as well. My bad, I forgot to literally put this part in early, and I want to make sure we have it all set up smoothly. I just noticed yesterday's lesson, some of those examples may have made it more confusing for individuals, so I figured this would be the best way. So if you want to go ahead and adjust what I had as line 14 here, where we made our classification, we're just going to make that into a definition. And I updated that in the repository there as well. So we're just going to do all definitions with this. That way it just gets a little bit smoother. I'm going to go ahead and just rerun that. Awesome. So I'm going to take about a 30-second pause here if you need to catch up on anything and get to make sure your code looks like mine. Don't necessarily need this one. So if you want to go ahead and cut that, you can. Again, that was more so exploratory there. All right. So again, just kind of reviewing what we've done so far. So we made a definition out of our getting the data set. That way we can just call it. Here we made a definition for getting our models, and then here we made a definition for evaluating them. So these three definitions we're going to combine together in order to make a nice little visualization here of seeing how these different models perform on the data that we made. So to do that here, we're going to go ahead and just make a nice little one block of code. So that's what I'm going to type, explain, type, explain. So we're going to go ahead and say we're defining our data set to evaluate. And what we're going to do here is we're going to say x comma y equals, we're just going to call that definition of get data set. Now, this get data set definition here, again, it's just going to apply this. So it's the same data set we've seen earlier, but by making it into a definition, it's just a little easier. So I could just copy and paste this whole line here as opposed to making the definition. However, we're going to try to get used to some clean coding examples here. So one thing that's great about writing definitions is it just makes your code really easy to read, and it helps kind of automate things too along the way. So it just makes it run a little more smoothly that way. And then let's get our next line here. We'll go ahead and say, let's get our models. So we're going to go ahead and just say models is equal to get models. So that's calling on this definition here. And again, we could manually do that. So I could say models is equal to, and then kind of type these out in a list. But in this case, it's just easier to build that dictionary up front. So again, the idea of getting used to this is just getting nice, clean, and readable code. It's also much easier to adjust things this way. I'll show another example of this later on, but when you build things out this way, it just makes it more reproducible for yourself as well. Because in this case, if I wanted to add models in, I could just go here, press enter, and then start adding models and then rerun that block of code there. If you try to combine all of this in just a one line, it just gets really hard to read and it's not as easy to edit either. Plus, if you want to use this in more than one space, by having just this dictionary we created with the definition, it also makes it easier to reference without having to change a whole thing. All right, next thing we're going to do is we're going to go ahead and evaluate the models and store results. Thank you, Larry. I appreciate that. It comes from much experience of making really ugly code and then being angry at yourself later. So that's where most people start to take really nice notes in their code like this, is once you've done something where it took hours to figure out. For example, I remember I made a matrix that would look for outliers. So I was looking for outliers along two axes, both population level and then within subgroup level, just to look for anomalous test questions. So that falls under psychometrics. And Python's a great way to build your own psychometric libraries and like analysis kits. But with that said, it's free. That's truthfully why most people would lean that way, as opposed to buying more expensive and paid, confusing software with very little customization. So I remember I spent hours, a good probably 20 hours in 1 week, just trying to create this like output matrix that would highlight and like give me all this cool summary data. And then the next time I had to use it with a different data set, I did not comment out my code very well. And it was just a very frustrating period of time for me to have to go back and figure out what every single line was doing. Because truthfully, in data science, if anyone tells you that they can just, guarantee they understand every single thing in a line of code instantly, that's not always the case. So working through good commenting practices like this will definitely help you out as you look back. All right. So when we're going to go ahead and evaluate into this, what we're going to do is we're going to zip these together with two lists. So we're going to go ahead and say results, comma, names. And then we're going to go ahead and say here, let's create two blank lists. So we're making two lists here of results and names, and I'm just calling them a list with nothing in them. So they're just nice blank lists there. Now you could just use the brackets as well there for the list. I like to just use the word list because then like I look at it, like I remember instantly it's a list, especially if you're someone who's new to coding. This is less obvious than what this is. So runtime isn't going to change on which one you use. This can be used in place to define a list. A lot of like, if you go on like Stack Overflow, that's annoying. Okay, get rid of that. So with this case, I would say do it this way, just because a lot of times like people who shorthand code a lot, it's just a little easier to read this way. All right, then we're going to say for name, comma, model in models dot items. So we're starting a for loop here to loop through these different things. So for name, comma, model in models dot items. And once we get through this whole thing, I am going to paste it in that online one as well, just in case you do get any errors. And what we're going to do here, first we're going to define what our scores are going to be. We'll say scores is equal to evaluate model. And we're going to say, look at our model, then X, and then Y. So we're using this up here and how we're evaluating our model. So we're just inputting those things. So these are inputs to that definition, a model, which is going to be each of these, and then our data X and Y. So we're using that last definition we created now. To get our results, so we're going to go ahead and append to that list. We're going to say results.append scores. So we're just going to use that list we created of results and then append the scores. So each time that model gets evaluated, we're going to go ahead and keep that and then create that list there with those values. And then we're going to go ahead and say names.append name. So it's just going to be these labels here. These are the names that we'll see pop up. We won't see this. We'll see these names here. And then lastly, we're going to nicely print it and format it. So we're going to say print. I'm going to go ahead and type this out and then talk through it. Okay, so what this is doing is just our for loop. So we're going to loop through by applying each of these, the different amount of times, and create those lists. This here is just a print statement, just formatting it nicely. For the sake of time in this, we're not going to talk a whole lot about how to use print formatting. However, it's basically just think of it as a way to print out certain things and make it look nice. So what we're going to get, what's going to be printed out is this is just the formatting piece to it. And then this is going to be what comes out. So we're going to get the name of our model. So which of these 5? We're going to get the score. So we just took the average there. And then we're going to get the standard deviation. So I'm going to go ahead and run that. Oh, what is it not like? So it looks like I spelled something wrong here. Yep, that should be a capital N. So this should be that. So if you had that lowercase n there, you can go ahead up. So this is something too we can talk through. When you see this, reading these errors, so it's telling me where it's at, saying, okay, hey, this is the issue. It's what as soon as we're touching this line of code, models here, it's having something go wrong. And then this was a nice one where it just told me like, look, like this is the issue. So again, it's not defined, meaning you need to rename the correct way. So that N should be capitalized. So let me go ahead and update that over here as well. So if you got that same error as me, you want to make sure your N is capitalized here. But I'm just going to go ahead and rerun that code. And then I can come on back down. So now when I run it, should be all good. And you're noticing this is taking a little bit, and that's totally fine. So what we've seen there, this is that output we should be getting. And by making that random state, we can see that if I continue to run this, so if I run it again, we're getting the same exact results. So even when I keep running this over and over, I'm getting the same results each time. So if I didn't have all of these random state commands in here, that would be where our issue comes from. So if I didn't have the get data set and evaluating model use the same random state, and the number 1 is irrelevant, you can choose whatever number you like, that would be where we'd have an issue here with this, where each time I run it would look different. Now, with these, we can kind of see like, okay, cool. So we get our averages. So the accuracy, that's we're implementing this on, is just based on accuracy. So we're seeing that how accurately it's classified into the different sets. And then it's showing us the standard deviation. So good ways to interpret this on a stat side. Stats are one of those things where it's like, it's all relative, I guess you could say, because what is a good average? That's something that a lot of students always ask, like, well, how do I know if it's a good average? I mean, the closer we're at to, like 99, like that would be great. But in a lot of cases, it may not also be practical. So what you're thinking about here, like I would say all of these are pretty good averages, but you obviously would want to take the best one that you could find. So that's kind of how that goes together. So right now, SVM is our best bet. It's got that 0.95. Reading into standard deviation, what you want to look there is that a large standard deviation means that like you had a lot of variety in your numbers. So these are the kind of 2 common metrics I'll use. Another way of looking at this is to look at a box plot as well. So let's go ahead and add a little more in here. So I'm going to backspace just so that I'm lined up with the for statement here. And what I'm going to do is just go ahead and plot this model. So to do that, we can say pyplot dot box plot. So I'm showing an alteration here. So you noticed yesterday in the code that people typically will use import matplotlib is PLT or .pyplot is PLT. Here I'm just showing in other ways. So this can be, if you were looking at a tutorial, you might see this is PLT. I'm just showing another way of doing it as well. So I'm going to try to have as much variability in the way we do things, only so that as you grow in your skills, you take other online courses, you look through tutorials, you have something to look back on that shows it's not always PLT. Technically, you can just do pyplot. And then when you use a box plot here, so we're going to say we're going to use the results. Labels is equal to names. And then let's go ahead where it says show means. We're going to go ahead and set that to true. And then I'm just going to say pyplot.show. So when I rerun that, let me go ahead and copy this over as well to our code repository. So now when we look, we have a little more of a cool output here. So we see this, and we also see the visualization piece to it. So when we're trying to interpret a box plot, the key thing there is looking at how, I guess you could say, spread out those are. So if I looked here at this cart, so what we defined a cart was our decision tree classifier. So again, I mean, we're not ranging terribly low here, but so these are placed vertically. So if I look, this one's got the largest standard deviation. And even though like the number itself may not look drastically higher than others, when you visualize it, it helps you kind of see like just how different it is. So I can tell off here, I had one anomalous outlier value here at that 0.7. And then I still have a pretty large, even if I ignored that, it's showing me that it's like, ooh, it's kind of skewed, right? So in this visualization here, these green triangles represent the mean of the data. So where we said show means is equal to true, that's what that green triangle is. This highlighted kind of yellowy line, that's our median. So if you're familiar with how to read box plots, this is our minimum, this is Q1 or quartile 1, this is the median, this is Q3 or quartile 3, and then this is the maximum. I prefer plotting them vertically like this just because it gives me a quicker way to read it. For some reason, I feel like when most people learn them, they only see them sideways. This is kind of the way I've always used them, just because it makes the data a little easier when you're comparing side by side to see it vertically as opposed to horizontally. So looking at these, I could kind of pick out real quick which two are doing the best. We could say KNN and SVM. So those two we can see. This one heads it out by a little bit, and they're similar in terms of their standard deviation. But again, I can see that SVM is a little smaller, and they both had those outliers. So they both had one round that just wasn't as good as the others. Whereas our LR and our logistic regression and then our Bayes don't have any outliers. So 3 had outliers. That's what those little dots represent, that it was just a little lower than the other values there. So at this point, what we've done is we've looked at each of these 5 individually. So we haven't yet actually done any form of stacking or putting things together. We just ran 5 separate models and we're comparing how they did. Now, in some cases, this might be like, wow, these are pretty darn good, right? We got a almost 0.96 here on accuracy. Like, do I need to stack? And the answer is, again, like, you may not always need to. If you can get a good way of, like, for me personally, if this was the goal, I'm like, okay, it's pretty darn good, right? Like, I could maybe even stop there. That's real low standard deviation. It's a good thing here. However, in a lot of cases, like, you may not get such good classification data. Like, you might be having trouble. You might only be in like 0.8 and like you don't feel comfortable saying like that's accurate enough for you. So what we're going to do now is we're going to go ahead and create some stacking. So I'm going to go ahead and type first, and then we'll walk through. So quick check in here before I put some stuff in here. So I'm creating a definition here again. We're going to be doing our stacking. So I'm going to take all 5 of these and use them in conjunction. So I just use level 0. So I'm referring to that level 0, meaning these are our level 0 models. And then what we're going to do here is go ahead and say what our list is. So I'm going to create a blank list, and I'm going to put all 5 of them in. So say 1, 2, then I put 1 too many. So I'm just going to append that list with these different things. So here, I'm just going to go ahead and copy some code just to have it handy, so I avoid any of those spelling errors that I had before. Okay, so let's see. I need this, each of them. So I'm just going to use the same naming conventions here. And this is, again, why I do try to focus on the best practices and then making sure everything's very readable, just because you want to avoid mistakes when you can. Also, for future reference too, these names are totally whatever you want them to be. So you can literally call them whatever you want or whatever shorthand you are. I've seen some people get really creative with them, like to kind of make their code look more like customized and like, only they can read it type thing. But those are just the ones I use. So again, totally up to you what you want yours to be. But you'll notice like this, like I like to put space in between there, and that's totally not necessary in any capacity. But I just like my code to be very readable, and then it's kind of formatted nicely where if I look back at it, I know exactly what it's saying. All right. So that is our set of stacking. So we have all 5 of those that are being appended. So here, we're going to go ahead and pick out our learner model. So I'm just going to choose logistic regression for this. The reason why I'm picking that one is because it performed a little better than Bayes. So it's slightly higher, but there was no outlier data. So even though when you look at these numbers, it seems like, well, these two especially are really, really good. However, sometimes when we see outliers in there, it just means that model might have a little bit of an issue. And when you run the model, you definitely don't want it to have any of these in there, like if you were trying to make a good prediction. So I always suggest when you're picking a learner model, use the one with the most normal distribution and with the highest average. So here we can see a nice normal distribution. So how you can tell that is going to be when the green triangle, which represents our mean, and the yellow line are in the exact same spot. So we used logistic regression here. I could use Bayes, it's also pretty good, but I'm going to choose this one, just kind of a little bit higher of an average than that. So choose that learner model. That's kind of the logic behind that. So I'm going to go say level 1, and I'm just going to go say is logistic regression. And then we're going to go ahead and define how it's going to stack. So what I'm going to say is model is equal to my stacking classifier. My estimators are going ahead and be level 0, so my individual models there. And then the final estimator, I'm going to go ahead and say is my level 1. And then the number of cross-validation, so how many times I'm going to go through, is 5. And then lastly, I'm just going to go ahead and say return model. So I'm going to go throw that in the repository here and then pause for a minute to make sure everyone's caught up. So that stacking classifier, that's something you'll commonly see whenever you're using this. So stacking just means we're going to kind of, again, layer our ensemble there. So it's going to learn from all 5 of those previous ones. Ooh, and I just realized I did something weird here. So let me fix this real fast. So that's the importance of always rereading your code as well, is that it's easy then to find your mistakes. So I wanted that to be my blank list, and there we go. Bad expense. So 1, 2, 3, 4, 5. Perfect. Okay, let me go ahead and update that as well in our resource file. There we go. Now that makes sense. Okay. So this creates our blank list, and then these are the 5 models we're appending to it. So it's a little different than the get models one we created earlier. So again, we're seeing this being a little different here. So this is how you would go about stacking. And again, you could add as many as you like in here. We're just going to stick with the 5 we've seen so far. So if you only like 2, maybe I want to get rid of some. Maybe I really didn't like this one here, and I'm like, we don't need the decision tree classifier. We can get rid of that because it didn't perform very well. But again, more is often better. But again, if you want to make the decision to say like, okay, let's comment this part out, we don't need it kind of thing, that's okay. All right, let's go ahead and bring in now. We need to change our def for getting models. So I'm just gonna go ahead and copy and paste it up here. I'm just gonna add to this. So if you can copy and paste it, so what you could do is you could add to it here. So if you want to include the stacking model, you could. However, just to kind of make this read well, I'm just going to copy it and then bring it down here. So after base here, what I'm going to do is I'm going to go ahead and put another model in, and I'm going to say models. I'm going to call this my stacked or stacking, and I'm just going to say it's equal to get stacking. So I'm referencing this definition up here. So while I could go change it at the top, the only reason I sometimes suggest copying and bringing code down is because if I were to run this, so let's pause for a second here, and I'll come back just to explain this important piece here, is that if I go way up here and I run this, so let's say I had that extra line of there of the get stacking, it'll say it doesn't exist. So it'll say like, okay, I don't know what get stacking is not defined. So whenever I update a definition, I do bring it down again to the bottom. So using that copy and paste feature, because a lot of people are like, oh, let me go back to the top and just add it in there so it is smooth and I don't have repetitive values. That's cool, but because we're kind of building this out as we go, I think it's best just to kind of update things vertically. So here, like, okay, I'm changing something, I'm creating a definition of getting a stacking. When I call that model, I want to make sure that vertically speaking, that call comes after it so I don't get any errors. Okay, so let's talk through these two again. I had a couple in the chat let me know they want to go through it. So in this case, what we're doing here is with this stacking, we're creating a learner that's going to use those level zeros. So my level 0, I created a blank list. These append statements, all 5 of them, what they're doing is they're adding these to that list there. So we couldn't use our previous definition there because, again, we wanted to build this all in together. So I called it level 0 because each of these isn't learning from anything. They're just the same models. So these models are going to look exactly the same as this. So that's putting those in. Right here, I'm choosing what I call a learner model, or the model that's going to take advantage of the others and learn from it. I chose to start with logistic regression. You could use any of these. The main reason I chose logistic here is just because it's pretty normally distributed, meaning my spacing in between my 5-number summary, so these 5 vertical lines, is pretty darn close. And it's very normal looking in the sense that my mean and my median match up. So that green triangle and that yellow line or orange line are overlapping. It also didn't have any outliers. So even though KNN and my SVM performed better, they did have outliers in there. So when I choose a model to gain knowledge from others, I try to choose the one that's most normally distributed and with a higher average. So I chose this one because it had a little higher average here than Bayes. What this is going to do here, so once I defined it, I said, okay, my level 1 is logistic regression. And so it's just defining it as that using that model. And then here is the model of the stacking part. So by calling the stacking classifier, which we imported way back when at the start, here are the number of estimators. So what it's using to get things from, I'm saying is these 5. So it's going to learn from all 5 of those. So even its own previous iteration. And then I'm going to say the final estimator. So it's going to be this one here. That's my level 1. And then CV just is the number of cross validation. So how many times it's going to execute this. And we just chose 5. That's a pretty common number. Like I said, some people get crazy, like when I used to, and put like 100 for that. It would just take really, really long for the program to run. And it honestly didn't improve results very much. So I choose like 5 as a good sample size there. And then return model just tells it how to end this definition. And our next one, for get models, we copy and pasted it from the top just to update. So I should go ahead and put that in there as well. So all we did here was we called this new model in here. So we had our previous 5, and then we looked at our stacking model where we said calling, it says equal to this thing. So it's calling that definition. All right. Now, let's see what we got here. So we already have our getting data set. We already have our getting stacking. So I'm just making sure we didn't change anything else. Okay, we didn't do anything with the data set. So it's the same exact data set. Same, we updated our stacking and that. We don't need to evaluate any differently. That one's still good. So what we're going to do is just go ahead and do some copying and pasting here. So I'm going to go ahead and just copy and paste this. And we're just going to rerun it. So again, this is kind of the nice part about using definitions like we have, because now I don't need to change it. If I try to put this all in one block, it'd be really hard to show you guys on screen. And also it'd just be a lot of going back and typing. So I'm gonna go ahead and rerun this now. So it's gonna get my data set, which we used a random state for. So that means it's the exact same one. It's going to get my models, which is right here using this definition. So it's including this one this time. It'll make the same list. So this is going to be the same way to evaluate those. And then here, we're just going to visualize it. So I'm going to go ahead and run it. And you'll notice we now have our stacking included. So it's all the way on the right. So it does just go vertically. Like if you want to put stacking in the middle, you can just put this literally in the middle here. I just put it at the end just because that was the easiest way to type it in. So when you get these models, like the order here is the order they'll be shown. So you'll notice this vertical order matches the horizontal order here. This technique really sounds great. In real-time problem statement as a data scientist, when do we really need to go for ensemble learning techniques? So this is a great question here, as when do we actually need this? And that's something that I think is really important whenever you're learning a new skill in data science, is seeing a practical application. So I can say from my own experience, when I've used stacking, because truthfully, I think this is a great thing in the point that like, if I compare these two, like it's not that much better. Like if I'm looking at the stacking, it's 965. Little lower standard deviation than SVM. So the one cool thing is we lost that outlier. So if I compare just these two of SVM and stacking, this is gone. So we no longer had any outliers in our data. So the stacking model would be best here. It's even kind of skewed toward the top, like it's not perfectly normal, which in this case, since it's skewed up higher here, we're good with our median, most of it being up here. So this is the optimal model in here. We see it's definitely better than all the others. There's no outliers. It's got the highest average and the lowest standard deviation. But as far as when you would need to use this, so it's one of those things I would say, like, the more you use it, the better, only in the sense because it really is going to build you your best model. And that's kind of the general idea of stacking, the idea that the more techniques it can learn from, the better it's going to do. So an example of when I've used this in the past is I learned about stacking when I started realizing that with like real world data, not every individual model is going to be enough. So for example, logistic regression is one of the go-tos. You'll see a ton of stuff on if you go online and type in, regression tutorials or classification tutorials. Logistic regression has the ability to work with a lot of different data and still be pretty accurate. So a lot of people go to that. However, the idea of stacking is just to improve our results and to remove anomalous behavior. So for example, with this k nearest neighbors, here we're looking at that classification technique. So the classification being is we're looking at things and we're trying to put them into certain bins. So in bin 1 or bin 2, whatever it may be. So a good way of looking at this is if you're validating a company and looking at sales, you may have your high sales, your low sales, and then like kind of your average people. So if you're looking at predictors for that, you might be looking at like information you have on your employees. So this is a great way of kind of predicting who you want to fill certain roles. Why I reference stacking as the best is because it's going to give you that where you can pull out in the good parts of each model, and it usually gets you where you don't have any outliers. And that's always the toughest part, is you don't want to have the outliers in your final model, despite these both being pretty well performing otherwise. So where I see ensemble learning coming in is that anytime you're doing a predictive analytics or a machine learning problem, you want to go ahead and then think of how you can make it the best that you can. So that's where I see, ensemble learning is like that next level of knowledge that really helps you kind of get better models than other people, truthfully. It's really getting the idea of that AI or like machine learning from machine, as opposed to just, running them individually type thing. All right. So what we did there, we went and worked this whole thing through so far just for classification. And again, classification is when you're trying to use data to assign things to a category or a bin by some type of, we think about it like a textual label. So like different categories we're sorting into. The other popular one is going to be regression. So what I'm going to do is I'm going to go ahead and just change this cell from code, and I'm going to go ahead and just make some markdown here, or you can do a heading. Just say, okay. I'm just going to say above example was all classification. Below example is regression. So if you go and download notebooks from online, you'll see this like nice heading notes there. And then you can just switch that up here with code, markdown, and heading. All right. We already have all our imports in from the top. I'm just going to go ahead and make sure I have these. Where are we at? Yes, okay, fantastic. I was making sure I had all the same ones already in the top. So with regression, we're going to use some different packages as well here. So we're going to create some new definitions. So what I'm going to say here is I'm going to make a new definition of getting my data set. And I'm using the same names here just to keep it kind of consistent so that we know what they're doing. The only difference here is going to be the one that we're calling on. So instead of make classification, I'm going to use make regression to get some data. So for this one, we're actually going to just kind of type this all together into one just nice large block of code here, just so we can kind of see that we can do it all in one if you'd like to. And then we'll kind of talk about the preference of like using separate blocks versus using a single block, whatever it may be. So for this first one here, we just have our definition of get data set. So I'm just making a new one. Before it said make classification, here we're making a regression. So the sample is 100, same numbers of features and the number of informative. Noise is another thing we can use here. So I'm using 0.1. It's just saying noise is like I guess you could say challenging patterns in the data. So like how hard it is to predict with. So the more noise you have, the harder it is. And then let's make a new stacking here. And then let's see, we'll get our base model. So let's go ahead and say level 0 is equal to a blank list. And for this one, let's try it with just maybe like 3 models here, just to make it a little quicker. So we're going to go ahead and say, let's see, parentheses again. And I will pause and go through this again once I get it through. Okay. So this should look pretty similar to the one we did where we created another get stacking. And again, the names of these are actually just totally whatever you want them to be. So if I was going to use all of this code in conjunction, you would want to change these names. So for example, up here, you don't want to use the exact same names if you're going to use it in conjunction. But since we're going through a demo, I'm using readability over here. But if you want to like put a 1 at the back of these, or maybe just get data or something, or get data regression, whatever you want to do, you can change those. I'm just kind of using it so that if you were to read through this, you'd remember what it does. Oh, wait, no, actually, my bad. So that's what I was going to explain next. That should be SVR. So what this is doing here That's a great point that we just made there. So the reason why that's an R is it's going for regression. So SVC is for the classification. SVR gets us into regression. So you'll notice the naming conventions here. So before we had K-neighbors classifier, now it's regressor. And then decision tree instead of classifier is now regressor as well. So that was a great observation there. Also a super common thing that when you're going through these, so a lot of online tutorials, you might go up and say, hey, like teach me how to do classification or teach me how to do regression. So the naming convention of a lot of these things is really, really similar. And a lot of times at the back end there, it either says classifier or regressor. So you want to make sure that you're using those right models. So thank you for that, because yeah, not gonna lie, I made that mistake myself a bit there. So yes, we're using SVR, so it's standing for the regressor there. So regression just means the idea of the predicting an output as opposed to the idea of predicting a group. And then here, for this one, the reason I'm using linear regression is that's usually one of the best bets for a level 1 model. The reason why a lot of people do still kind of stick to linear regression, even though it doesn't seem as cool, is its usability and practical implications are really nice because it is such a simple model to work with. And then here, same thing, we have a stacking regressor as opposed to the classifier. I'm gonna go ahead and put that over in our notebook here as well. And then what we're gonna do is we're gonna update our get models. So I'm gonna go ahead and make another definition of getting models. And then here, I'm gonna say models is equal to a blank dictionary. So that's our definition there. So again, we're building this all into just one block of code. So this would be something you could do as well as an extended exercise with your classification, attempt to make a singular block that does everything. So putting all of our definitions together, I'm just reading through it on my side right now to make sure I don't have any typos. And that I didn't forget to put return models at the bottom. There we go, return models. All right, now let's go ahead and get our model evaluation here. So we're gonna say def evaluate model. So this right here, this cross fail score, that is a call, so it does have to be typed exactly like that as well. And I'll explain what that is in a second there. So with this one here, what we're doing is we're going to say how we're evaluating our model. This looks really similar to what we did before. The main difference here is how we're going to look at the scoring. So what we're looking at here is the mean, the negative mean absolute error. So this is a common one when we're dealing with regression. You can use others. So if you want to look up different scoring options, let's see. Let's see if I can get you guys a resource on that real quick while we're typing that in. And actually, to make this a bit simpler, let's go ahead and get rid of this. And we're just going to say we'll use R2 here. Mean absolute error is cool, but we'll see in a second here how this can work. And what that link took you to was this website. So this is something I would definitely bookmark if you haven't, just because of the fact that like it's all these definitions. I mean, I'm actually going to bookmark it on my side too, so I don't have to keep Googling it every time. So what this is all the different metrics as well as how their scoring is used. So if you're using a classification, we used accuracy. There's some other ones here as well. And there's some summary tables that list out a lot of this as well, but it's just nice to be able to decide in there what to use. So this would be something that you definitely want to save as a resource for classification scoring. When you do clustering, here's some other options as well. And then we won't have time to cover clustering today, but it is something that's going to look similar. And then regression, here's all your options here. So I chose R2 here. So if I click on that, my metrics of the R2 score, it takes me here to an explanation of what it is. So if you're ever looking how to use these scores, Scikit-Learn does have a really cool, very nice library of what all this stuff is. It also tells you how to use it. All right, so let's get this finished up. What we're going to do now is just do our last thing here, which is getting that cool visualization with it. So I'm going to go ahead and pause for a minute, get some typing done, and then we'll talk through our model. And I'm just kind of shorthanding this a bit more just because it's the same one we did earlier. So I'm just kind of making this more able to fit on the screen. So I'm not going to do as many comments in here as I typically would. And I'm actually just going to go steal this one from up here because that one's kind of a pain to copy and type. All right, so let's see, where are we at? So I'm checking errors in mine real quick here. Let's see. I didn't say return anything. There we go. So return x comma y. So I'm just going to make sure mine executes and is error-free before I have you guys explain it. Fantastic. Okay, so let's go ahead and talk here a little bit about what this is going to look like and what it does. So going line by line here, let me go ahead and throw this in the repository we have first. So if anyone needs to get that over, that is that whole block of code I put in there now. So in this case, again, we're looking at regression here. So first we're going to make our data set. That's what this line is up here. And what I had forgotten to type in there was this return XY. So when you make a definition, it does need to end with something, whether it's a return, a print statement, whatever it may be. So I forgot that line, and that's why it shot out that error the first time there. So it's telling it what to return. Here we were walking through our stacking technique of getting that stacking. So we started with a blank list here for level 0, and then we appended it with these 3 different models. We then chose linear regression as our learner model. So that's going to be the one that learns from the previous 3. Then putting that up, used a stacking regressor instead of a stacking classifier. And then we had level 0. These are our level 0s for our estimators. And then the final estimator that's doing all the learning was going to be our level 1 there. And then our cross validation we set at 5. So to run this thing 5 times for each. With that number, again, you can make it more, but like usually 5 is just a solid number that doesn't do just too much and take forever to run. Here we're making our models, so we have a dictionary created. So here's the 3 models by themselves. And then our stacking, which is what we created up here. So we use that linear regression and having it learn from those 3. Right here with evaluating our model. So model X and Y. Here's our splits and how many times we want to do it, and then our random state 1 just for consistency. Here's our scoring method. So we chose scoring of R2. And if we look at what that R2 is, go ahead and get that open. Just to talk through that R2 there. Because this is something too, I feel like a lot of people may have trouble with when they get into data science, is the statistics side to it. So knowing like how to interpret these things. So here, this is for just getting an R2 score directly. We've seen that yesterday when we were comparing our output at the end. Here's another way that we can call it in models like this. So it looks a little bit nicer. So it's the coefficient of determination. So you'll hear it is an R2. It's technically, we should say R squared, but everyone kind of reads this as R2. So it's used with regression. So our best possible score is at 1.0, and it can be negative because the model can be arbitrarily worse. So again, like it's from positive to negative with 1. We're looking for that 1 being our best one there. And then a constant model that always predicts the expected value, disregarding the input features, would get a 0. So what this is, we could think of it's the amount of variance that can be explained. So again, even if it always gets it right, if it could ignore all of the data essentially, so all the different features within the data, then that would be at 0. So our best one here is we're looking at 1.0. So if we get close to that or even relatively high, it's pretty impressive. Here, you can see all the input differences here. So the true versus the predictions here. If there's weighting involved, if you want to get multiple outputs, so on and so forth. So again, reading through these things, you can kind of see here the differences of what you have. And then there's always some sample code in here usually too of like seeing it in use of what you can get here. And then here's some other examples too. You can kind of click through and see as well. So definitely a cool resource to have handy. So that's where we're at there. And then this is the part where we're actually going to get our model. So this is really, really much the same as we used up top. So this is something, again, you may want to save and be like a nice little copy and paste tool there. So then when I ran it, we could see our output coming in. And you see that it got stuck there for a second. So when I run that, you can kind of see the process. It gets stuck here while it's executing the stack for a second, and then it goes through. So let's talk a little bit about this one here. So we see our 4 models in here, and we can see that some of these aren't really doing a whole lot for us. In terms of our R-squared scored, again, higher is better. So we see this stacking is like fantastic, right? We're at 0.877, pretty low standard deviation there, even though it's a bit higher than some of these. Like it's a little higher than the SVM, but SVM also performed terribly. So when we're looking at these outputs, standard deviation looks for consistency in the model. So lower is better. That means it's at least all together. But SVM here, even though it had like our lowest standard deviation, it was also a terrible model for this. Like our R-squared score was super low. KNN did pretty good on its own, not quite as good as the stacked version. And then our one here, our decision tree regressor cart, pretty bad, right? At 0.221 is an average. So again, we can kind of see that some of these models just aren't really doing much for us, whereas SVM, again, just real bad here, 0.08. So when we run this and we see things are doing very poorly, it doesn't make much sense for us to learn from them, right? So let's go ahead and do a little bit of commenting on this code. So I'm going to go back and I'm just going to comment out. So I'm going to get rid of SVM and cart here because they don't seem to be helping me very much. So I'm just going to go ahead here. I'm going to still have them be in my models, but I'm not going to use them when I'm building my stack. So I'm just going to go ahead and put in here just 2 of these comment outs. So all I did was go back to get stacking and I put the pound or hashtag symbol there in front of those. So all it's saying is like, we're not going to use these anymore. Well, actually, no, not KNN. We wanted KNN. We didn't want SVM. There we go. So that's the way you can make it look there. So I just commented those lines out. So it won't affect actually the way my program runs. It's just going to say those are comments now. I also didn't delete them just because, like, you know, sometimes with a different data set, they might work really well. So you can keep them in that way. That way you don't have to, you know, keep deleting code. So once I have that, now what I'm doing is I'm using KNN and I'm having linear regression just to learn from that one. So let's see if that improves or hurts our model. Because right now our best one, if we look at our stacking, we're at 0.877. So let's see how that works now if I rerun this. Now, we can see these first 3 are getting those same kind of results here. However, now with stacking, we were at 0.877 and it went down even more. So now my average is at 0.688. So if we think about that, we thought like, okay, well, these look like bad models. Like, why would I want it to learn from them? However, even bad models can do something well and help them learn. So I'm going to go back and put those back in because we can see even though that they didn't perform particularly well themselves, my learner, my linear regression here that's learning from all of these was still more effective when it had everything to learn from. So I'm going to go ahead and bring those back in. And when I run it, we can see we get back to that much stronger result here. So that's something too, that even if models perform poorly, that doesn't mean that they're necessarily bad models. So maybe if I just get rid of this cart one, so I want to figure out where it's learning the most from. So it's learning a lot from KNX, that's the best performing model. But I want to see if one of these maybe I could get rid of just to simplify. So let's try if I get rid of just this one here, just a cart. So 877 is still our score to beat. And we go down to there we go, 873. So it looks like cart is kind of not totally necessary in our model. So again, that's where a little bit of experimentation by users. Again, you can play around with it, see which one is, you know, maybe necessary for things to work and which one is kind of helping you learn the most. Or you could try adding in additional models if you want to look at some of those other ones available there. But yeah, when we're looking at this, that's kind of where the user comes into play, is just the idea of taking certain things out, putting certain things back in. So if we kept them all in there, we can kind of see how that's improving it there. So again, even if a model by itself doesn't do that well, sometimes it can still be a learning tool for something else. So just once more in the chat, I'm going to go ahead and send this on out. So that's another way to get to all the code that we did today. It's also clean and pretty copy and pastable. However, I really don't suggest you just copy and paste. So again, if you were doing that today, again, working through these tutorials, getting your things yourself typed out is always the best way to learn that coding. So what you can be looking to do to kind of increase your skills even more is going to be trying this out. So what I'm thinking that'd be good is either pick one of them, classification or regression, and pick a data set that you choose. A great place to get these data sets is from Seaborn. They're free and it's pretty easy to import. There's iris, penguins. If you look for the iris data set, there's a million examples of classification using that. So let me go ahead and get this brought up. So this is all the cool Seaborn data sets here. So these are great ways of pulling things. And then if you're looking for the documentation on how to call it in, if you've never worked with Seaborn, here's some here. We'll use that in later tutorials as well. So it'll be a common thing that we see, but it's good practice to read other people's documentation as well. So what you can see here is where these data sets come from. So this is just a really easy way to pull in data. So Seaborn is a cool visualization package we'll use a lot with throughout these courses, but here's just some nice data that I like to use because it's cool for examples and it's consistent data. So you'll get those same results. So some of the common ones you'll see is iris. There's a ton of stuff out there. People love using this data set for demos. There's some very cool ones. Penguins is actually pretty cool. So that's one of the recommendations I had on here, just because it's a little more something, I guess, different from flowers. So that would be this information here. You could bring it in and you could try to classify by different things. So there's a couple of categories like sex, islands, or species, and you could use these, or you could try to predict maybe body weight based on these other variables here that are measures. So this would be using some different data as well. So that would be the goal, is that you use one of these tools. So things you wouldn't need necessarily, you don't need to get a data set here if you already have a data set. So it will change the way your code's going to look a little bit. However, like the stacking, the getting the models, evaluating the models, that would all be the same. The only things that's really going to change is your data set here, as opposed to that, you'll have to get your data cleaned up and ready to go that way.